This section is about continuity over an interval, and it's really just like solidifying some information about continuity. So first of all, there are some common functions that you've already worked with in your past that just everywhere they exist, they fit that three-part continuity test. So for example, polynomials are continuous everywhere. There's no x-coordinate that's going to mess up your limit. There's no x-coordinate that's going to create a vertical asymptote as long as you have a polynomial. Sine and cosine are continuous everywhere. So you can imagine that sine and cosine graph. It's a beautiful wave. You never have to pick up your pen as you're drawing it. So those functions are continuous for all x's. Exponential functions also are continuous everywhere. As you graph an exponential function, it has that nice slow build up and then zooming up, but I can sketch it on any x coordinate and it doesn't fail to exist. And the limit is always going to match the value of the function for exponential functions. Log functions are continuous wherever they're defined. So just a reminder about the general shape of a log function. The general shape of the log function looks like this. It has a vertical asymptote at x equals 0. So as long as x is greater than 0, my log function is going to be continuous. Rational functions are continuous wherever they're defined as well. Sometimes you wind up dividing by 0, then your function is not continuous. But if you're not dividing by 0, then your function is going to be continuous. Tangent, cotangent, secant, and cosecant are also basically rational because they have a division by 0 problem. And so they're also continuous wherever they're defined. So if I'm trying to determine when I look at a big, messy, complicated function, whether my function is continuous, I can say, well, that's exponential, that's a polynomial, and that's part of a polynomial. So yeah, it's continuous, but it's a rational function. So at x equals 0, I would be dividing by 0. That's a big no-no. And at x equals 5, I would be dividing by 0. That's a big no-no. So those are two places where my function doesn't exist because it's a rational function. So if I look at interval notation, I want to remind you about interval notation. This function is going to be continuous from negative infinity all the way up until you get to 0, not including 0 because it's not continuous at 0. And then it's going to be continuous from 0 to 5. And then it'll be continuous from 5 to infinity. The other way of writing that is you could say all real numbers such that x is not equal to 0 and x is not equal to 5. Please make sure you're using correct notation of some sort. So you want to be clear about that. Here's another function with possibly some discontinuities. So if x is less than 0, this is going to be the e to the x function. Well, I know that that is continuous all the way up until 0. I know e to the x is continuous. And then sine x plus 1, well, I don't know. Let's look at those two limits. The limit as x goes to 0 from the negative direction of e to the x would be 1. And the limit as x goes to 0 from the positive direction of sine x plus 1 would be, also 1. And f of 0 would be, I would use this part of the definition, so that would be 1. And since those all match, that's continuous at 1. X equals 1 is a point of continuity. And then I'm also going to look at pi. The limit as x approaches pi from the negative direction would be sine of pi. Well, sine of x plus 1. Sine of pi is 0, so that would be 1. And then the limit as x approaches pi from the positive direction would be negative 2x, but that would be negative 2 pi. So this is a problem. So our interval of continuity would be from negative infinity up until pi, and then from pi to infinity. And I know this continues to be continuous here because negative 2x is a polynomial function. I know it's going to be continuous. It's the only problem is pi.